Hello, everyone. Hopefully you can hear me okay. Thank you for having me. My name is Sam Gutierrez. I'm a member of the Application Readiness Team in the High Performance Computing Division at Los Alamos National Lab. Today, I'll be talking about a method we invented a few years ago to achieve adaptive parallelism for coupled hybrid programs, parallelized using a mixture of MPI and threading. Hybrid parallel programming models that combine message passing and multi-threading, for example, MPI plus OpenMP, are becoming more popular, meaning that application developers are increasingly porting or rewriting single-threaded message passing libraries to include multi-threading. And in coupled applications, this means that some phases use a hybrid parallelization strategy, while others are still using a message passing only parallelization strategy. The implication of this is that message passing only phases are now interleaved with multi-threaded message passing phases that have differing preferred degrees of threading per process, resulting in thread level heterogeneity. One typical example of where this type of coupling occurs is in parallel and distributed multiphysics applications. These applications are important because they play crucial roles in science and engineering and are interesting because they are often an interdisciplinary effort, meaning that they are often built by coupling independently developed and optimized software libraries into a single application comprising different distributed data structures and parallelization strategies. An example of this could be the coupling of a library that operates on adaptive structured mesh using message passing to, say, another that operates on a particle mesh using multi-threaded message passing. And ideally, we want each computational phase to execute in a way that is consistent with its design and tuning. That is, given a particular workload and hardware architecture, each library should run with its own optimal runtime configuration, which may include, for example, the number and placement of its tasks. If a phase is configured suboptimally, then its performance is negatively impacted, which in turn negatively impacts the performance of the application in which it is linked. Today, parameter selection is mostly static, as we have heard today, and this particular approach isn't ideal for a variety of reasons. A major one is that configuration conflicts, where optimal library configurations conflict with one another, are becoming commonplace in integrated parallel codes. Today's state of the practice mostly relies on static configurations that bind tasks to hardware resources. With one notable exception, Guillaume mentioned, I think he alluded to a project named Hippo out of Surfax. But since today's parallel launchers, say for example, srun or Orte-run, provide only static mechanisms to influence binding and placement of tasks onto hardware, the launch time configuration that is selected at application startup is the one that persists for the life of the application. And the two basic configuration options available today are either hardware oversubscription or hardware undersubscription. When using oversubscription, the number of subscribed processing elements, or PEs, usually this corresponds to the number of active MPI processes per compute node, equals the number of threads in the computational phase with the lowest degree of threading per process. In phases that require a higher degree of threading, resources are oversubscribed with multiple threads per PE, which is often suboptimal in practice because of increased resource contention. Because of this, the most commonly used approach to handle configuration conflicts resulting from thread-level heterogeneity is to undersubscribe hardware resources such that the phase with the highest degree of threading per process has one processing element per thread. Now, the implication of this is that single-threaded message passing phases run undersubscribed, using only a fraction of the available hardware resources, which can be problematic, especially if these phases strong scale well, for example. To address these inefficiencies, we constructed a model and built a corresponding system for dynamic runtime configuration conflict resolution. Our current implementation is built specifically for coupled applications based on the message passing interface, MPI, that employ additional shared memory parallelism using pthread-based runtimes. For example, OpenMP or standard thread for the C++ programmers here. Our system is named Quo, Quo is an open source runtime library that can be used to dynamically resolve configuration conflicts that arise in coupled thread heterogeneous message passing applications. Quo does this through an interface that exposes mechanisms to query hardware characteristics and task configurations that are then used to reconfigure the execution environment of a running application. And it does this in a performant and composable manner. And when we say Quo is general, what we mean is that it exposes two language bindings, is MPI implementation agnostic, and works with a variety of unmodified pthread-based runtime systems. And this includes raw pthreads. To understand our approach, let's look at 6 main concepts. The first being Quo contexts. Contexts are nothing more than opaque handles to Quo maintained state. They can be created from an arbitrary MPI communicator at any time after the MPI library has been initialized and destroyed any time before the MPI library is finalized. Multiple independent contexts may exist within a single application. Hardware and software environment queries are used to effectively guide application-specific hardware affinity, to guide application-specific software affinities to hardware resources. They include hardware topology queries that provide hierarchical hardware relationships, which are for the most part just thin wrappers around commonly used HW loc routines, and intra and intertask state queries that provide insight into how MPI processes are currently bound to hardware resources. When combined with application-specific heuristics, we can then enact process binding policies by using dynamic process affinities that are exposed through a simple stack-based semantics, where before a new phase is entered, we can push a particular policy, execute in that new environment, and then revert the policy by popping it off the affinity stack. With these semantics, a user can stack an arbitrary number of binding policies that map to the potentially stacked composition of coupled components in a Quo-enabled MPI+X application. To make our approach maximally effective, there must be a portable and efficient mechanism for quiescing sets of MPI processes to yield their use of compute resources, to make room for more threads of execution in multi-threaded phases. In Quo, this node local mechanism is called a Quo barrier. I won't go into the details here, but our papers detail the need for this seemingly redundant call. It basically boils down to MPI-provided facilities such as MPI barrier are simply too aggressive and therefore introduce too much application perturbation. Before the number of active MPI processes can be safely increased or decreased, data must be exchanged among node local processes to satisfy all inter-process data dependencies. Typically, this occurs via node local gathers and scatters before and after Quo-enabled regions. Once dependencies are satisfied, Quo can enact arbitrary task reconfigurations. And finally, policy management is concerned with who, meaning the caller or the callee, is responsible for the policies that influence how logical software affinities are mapped to hardware resources. In this particular example, we can see a caller-driven approach where the caller modifies the callee's runtime environment and assumes responsibility for resource selection. That is, the computational resources to be used by a particular computational phase, MPI process selection, so the set of MPI processes that will use the selected resources, and process affinity selection, that is, pushing and popping binding policies as the target library's computational phases are entered and exited, respectively. Now that we have, we've presented all this, now what is the cost of all this runtime intervention? And is there actually enough reclaimed parallelism in practice to justify Quo's overheads, both in terms of runtime overhead and development effort? To answer these questions, we devised a microbenchmark and also integrated Quo into real parallel applications. For the sake of time, I'll skip the microbenchmark results and focus on the achieved performance of our approach using 3 real production codes that employ a variety of parallelization strategies, running 30 different workloads atop different hardware and software environments. We believe that this diversity demonstrates the generality of our approach, and please keep in mind that our evaluation here is against what is used in practice today, namely static undersubscription. Of these workloads, 26 cases show an overall speed up, where over half were sped up by at least 20%, by more than 50%, and 20 out of the 30 cases showed an overall speed up of at least 20%. The max observed speed up in this study was approximately 5.8x, and finally, 4 of the 30 cases in fact demonstrated slowdowns. There are 3 main reasons for this. The first is if the undersubscribed phase does not strong scale well, Quo's approach will not yield a significant performance boost. 2, Quo can increase the cost of data domain remappings. And 3, in some cases, Quo appears to add some overhead to the fully subscribed computational phases, and we're looking into that. For more details about this study, please consult our 2017 IP-DPS paper cited below. And as with everything in life, nothing is free. With the quiescing and later resumption of tasks, application data remappings across library domains may increase. Also, when using our approach, one must identify and surround computationally intensive code regions with calls to Quo bind push and Quo bind pop. And finally, in order to apply dynamic affinity scheduling to something other than Linux processes and pthreads, similar interfaces and mechanisms that influence how they are scheduled must exist. And that's sort of a systems programmer problem, but I thought I'd mention it to the domain scientists. For details, please consult the manuscript provided below. In summary, coupled applications increasingly comprise message passing libraries with differing preferred degrees of threading. Static execution environments are often suboptimal for resolving dynamic phase configuration conflicts. And Quo's approach can help improve overall application performance with the dynamic execution environments. Thank you very much.